That previous theorem makes example 3 significantly easier. It says the limit of a rational function. Find the limit as x approaches 1 of x squared plus x plus 2 all over x plus 1. Well, this is a rational function. And for rational functions, what we're able to do is simply plug in the numbers. Plug in the x values. So this would be 1 squared plus 1 plus 2 all over 1 plus 2. Or sorry, 1 plus 1. Everywhere you see an x, we're plugging in 1 because we wanted the limit as x approaches 1. Whatever that number is the number that you plug in. Okay? So let's do the math here. 1 squared plus 1 plus 2, I'm getting a 4. On bottom, 1 plus 1 is a 2, and 4 divided by 2 is 2. That's our limit. No work other than that needs to be shown, and you're done. In fact, you didn't even need to show the 4 over 2 step because you could have put it in your calculator and gone straight to the answer 2. I would have been fine with that. I absolutely need to see this step of work on your when you show your work. And remember, for the test, you do have to show your work. I do need to see you evaluating that limit. I need to see you plug in that x value to every single one. So make sure you're at least showing that step for me. Okay. So that's for polynomials, but what do we do for radicals, square roots? Remember, square roots, cube roots, fourth roots, etc. How do you handle it for radicals? And that's what theorem 2.4 is about. It says the limit is, or let n be a positive integer. The limit below is valid for all c when n is odd, and valid for c greater than 0 when n is even. So what are they getting at here? For square roots, if you remember, whatever's beneath the radical has to be positive or 0. If you try to find the square root of a negative number, for instance, the square root of negative 4, you might remember that it's something like plus or minus 2i, okay? Or you can have some i's there. So is that a real number, though? And the answer is no. So anything with an I is not a real answer. So the square root of negative 4 is not real. It doesn't exist. So that's all this is doing, is it's saying anytime you're trying to find a square root, a fourth root, a fifth root, you've got to make sure whatever's beneath it is greater than or equal to 0 to be able to plug it in. But if it's an odd root, it's perfectly fine. For instance, the cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So if it's an odd root, cube root, fifth root, seventh root, ninth root, so on, it can be positive and negative. If it's an even root, it has to be greater than or equal to 0. So that's what that first part says. The second part says, what is the actual limit? Well, the limit as x approaches c of the nth root of x is the nth root of c. In other words, for radicals, you can just plug it in. So let's go ahead and write that. For radicals, simply plug in the x value to evaluate the limit. Provided it exists. So again, when I'm saying provided it exists, I mean no square roots of negative 4 type thing going on there, okay? Theorem 2.5 is a nice one as well. It's about compositions of functions. Remember, we did evaluate compositions of functions in the algebra lines and, in the lines and functions review. We did look at compositions of functions at the very end of that packet, so you should be familiar with that. And all it says is if you want to find the limit of the limit of a composition of functions, plug that value into the inside function first. Whatever you get from there, plug it into the outside function, and that would be your answer. So just like you do with compositions of functions, plug it into the inside function first, then plug it into the outside one. And just to let you know, this would be something like 2x plus 3 quantity cubed. If we wanted to know the limit as x approaches 1, all it's saying is plug it into that inside function first and then cube it. So that's a rule that in a sense we already have, but it will help us when we do things like limits of trigonometric functions and things like that. This is the theorem that allows us to plug it into the inside function first. So I'm going to go ahead and erase that example right there. Again, remember, you can download that Wolfram CDF player, and when you do that, you see the link to the problem, so you would click on that link right there. You would go to that problem, you could download the file, and then open it up with that CDF player, and that's going to let you tinker around with this. Now, you don't have to do that to understand the answer to the problem, but if you're a visual learner, playing with those CDF player and those examples will be really nice. You can evaluate the limits of that function at different places, so it's kind of cool. And you get to visually see what's going on. But this one says, 4a says, find the limit as x approaches 0 of the square root of x squared plus 4. Well, because it's a radical, because of our rules, we know this has to be equal to the square root of 0 squared plus 4, as long as that exists. Well, that's the square root of 4, which is simply 2, and I'm done. Again, you're going to have many times this semester, for almost every problem, I am not putting my answer in the answer blank because I don't want to scroll over and do it every single time while I make these videos. But you are required to put all of your answers in the answer blanks. So make sure you put the number 2 in the answer blank for me. Okay? Doesn't work just for square roots, works for cube roots, works for any root in all honesty. It says find the limit as x approaches 3 of the cube root of 2x squared minus 10. Well, that would be equal to the cube root of 2 times 3 squared minus 10. Just plug in that given x value. 3 squared is 9. 9 times 2 is 18. 18 minus 10 is 9. That's not right. Is 8, right? 18 minus 10 is 8. What's the cube root of 8? The cube root of 8 is 2. So the answer on this problem would be 2 as well.